Hello and welcome to the additional mathematics course. Today we are going to start a new chapter on logarithms. So that's chapter 3 from your additional mathematics book, and it's on logarithms. Okay, so let's just consider some easy examples. So 2 raised to the power 2 is 4. It's obvious. 3 raised to the power 2 is 9. 3 raised to the power cubed, 3 cubed is 27. But what is, or rather what should three be raised to get 19683? So you can write this statement down as 3 to the power of x. Let me make x better. Equals 19683. And what is x then? So one way to do it is by taking logarithms. So we can write this statement here as log of 3 19683 equals x. So this doesn't explain anything. So what is a logarithm basically? And right now we'll just define it very, this is not a formal definition of what a logarithm is, but for our case we can just define a logarithm to be a tool that computes, okay, that's not very well written, a tool that computes the power or index, as some like to call it. So in a general situation, if, let me change the pen color here, let's go with green. So in general, if you have a greater than 0, not 1, a cannot be 1, then ax equals y is just the same as writing log of a y equals x. And this is pretty much what we've done in this case here. If you look at this and if you look at this, you see what you see is that in the previous case a was 3 and y was 19683. If you can't see that, let me just write it here. A equals 3 and y equals 19683. And then what you got from the previous example was this log of 3 19683 equals x. The logarithm, once again, is just a tool to compute the power. Here we see that x is log 3 of 19683, and x over here was our power that we needed to compute. We'll do more examples of this and hopefully it'll get more clear for you. So if we want to know to what power should we raise the number 2, hold on, let me change the pen back to red. If you want to know what power you have to raise the number 2 to get 56, we can write this down mathematically as this, and then using our rule, which was a equal what was it, 8th power x equals y, is exactly the same as writing log of a y equals x. This was our rule. And this is basically called the index form here. We can write this down in log form as log base 2 of 56 equals x. Another more relatable example would be if you have, for example, 3 raised to power 3 equals 27. You can write this as in log form as log base 3 of 27 equals 3. Another example would be 4 raised to power 2 is too easy. Let's take 3, and that's just 16 times 4, 56. In log form, this is the same as writing log base 4 of 56 equals 3. We can also have, I don't know, something like 7 squared, and that's in log form, the same as writing log base 7 of 49 equals 2. And don't worry about it if you don't get it by now. We'll have plenty of examples in this lecture where you will see this index form being switched to log form and log form being switched to index form. One thing to note here is that, the base, which was this a here in our previous slide, that has to be positive. Okay, sorry, hold on. Log form is given as x equals log a of y. So our base, this thing here is called the base of the logarithm, base. Okay, this base a has to be greater than 0, it has to be positive, and it cannot be equal to 1. So why can it not be equal to 1? Well, if a equals 1, let's try if with a equals 1. So if a equals 1, then, well, 1 squared is 1, and 1 cube is also 1, and 1 to the power of 4 is also 1, and 1 to the power of 5 is also 1, 1 to the power of 70 is also 1. And now we can convert all of these to log form, and we'll see why we cannot have 1 as a base. So in log form, this is just, well, log of 1, 1, 2, log of 1 1 equals 3, log 1 of 1 equals 4, log 1 of 1 equals 5, log 1 of 1 equals 70. And from this entire set of results here, we can see that log 1 is of 1 is not defined. There's no unique answer to this. That's why you can't have a base of 1. It never really gives you a unique answer. So another thing to remember is this, that if not if, but just as a rule, small tiny rule, log x we have a to the power x equals y. Log form, you write this as log a of y x equals this. A has to be greater than 0 and a not equal to 1. Okay, so let's move on and let's see some more examples. Get used to this index form being switched to log form. So another example would be let's try 11. So 11 raised to the power of 7, that's 19487171. If this number is not accurate, just correct it for yourself. This example is just to give you the point. Log form, that's just log of log 11 of 19487171 equals 7. Another example would be 5 to the power of minus 3 equals, what is it, 1 to the power of 5 cubed, that's 1 over 125, 8 to the power 10 to the power minus 3. So in log form, you can write this as log of 5, 1 over 125 equals minus 3. Okay, I really can't think of more examples at the moment. I hope this is enough for you. If not, don't worry, we'll go through far many more examples in a few more minutes. Okay. Another thing to note is that when you write a to the power of x equals y, and if a is greater than 0, then y must be also equal to 0. If this statement is obvious to you, then that's very good, but if it's not, then let's go through this step by step. So what are the constraints on x? So x can be greater than 0 or x can be less than 0. Basically, x can be positive or x can be negative. Let's try what happens when x is greater than 1, and let's try with a equals 3. Okay, so 3 to the power of x is then greater than 3 to the power of 1, since x is larger than 1, and that's 3 to the power 1 is just 3, and that's greater than 0. Okay, what happens when x is between 1 and between 0? Well, 3 to the power of 0 is just 1, and 3 to the power of 1 is 3. So 3 to the power x, in the case when x is between 0 and 1, is just greater than 1 and less than 3. In either case, we can see that 3 to the power x is greater than 0 again. So in our first case over here, the first case, 3 to the power of x was greater than 0. In our second case, 3 to the power of x is again greater than 0. So what happens when x is less than 0? That is when x is negative. Well, x is negative, then minus x is greater than 0. And 3 to the power of x can be written as 1 over 3 to the power minus x. And we know that minus x is greater than 0 here. So from our first two examples, first two cases, we can see when x is greater than 0, 3 to the power of x is greater than 0. So, and here minus x is greater than 0. So 3 to the power of minus x, which is positive, minus x is positive here. So 3 raised to that positive number is again greater than 0. And 1 is of course greater than 0. So our result is greater than 0. So over here too, we see that 3 to the power of x is greater than 0. So what we learn from this is that, okay, let me make it another color. Is that whatever you choose x to be over here, when we had a equals 3, y was always greater than 0. So let me go to a new slide so that I can write down more clearly. So 3x always greater than 0 for all x. You can try this with any number a greater than 0. Of course, don't try that with, you can try it with 1, 2, but you're just gonna get the same number 1 every time you try it. We see that if a is greater than 0, then 8th power, actually I recommend that you try it with other numbers as well. And what you see is that in general, if a is greater than 0, then ax is greater than 0. So ax equals y and 0, so greater than 0. So if I'm repeating this again just so that it gets into your head, a greater than 0, then ax equals y, and y is also greater than 0. Okay. So the next thing we'll talk about is when, let me switch the pen color. When is this logarithm defined? Like you have something like log of a y. I'll write it in an index form for you as well. Ax equals y, that's the index form. I won't write index form and log form all the time. It's just that we just start this new lecture and I just want to keep mentioning it so it gets stuck into your memory. You can write this into log form as x equals log ay, and this is the log form. So when is this log ay defined? When is, okay, that's the question here. All right, so we just saw that if you have a positive, then a to the power x equals y is always greater than 0 for all x. Right? So y cannot be negative. That's one. And is there any other rule that you can think of? We can also write this down as y greater than 0. Another rule is that a cannot be 1 and a must be greater than 0. So the two rules are this. You want log ay to be defined, and 1 y greater than 0, and 2 a greater than 0, a not equal to 1. You must commit this to your memory, and whenever you see examples like, for example, let's write down like at least 4, a log 1 of 1, let's try another one, b log 1 of 3, c log 2 of minus 8, and d, let me write that down, doesn't look good here, and d log 7 of minus 3. So let's just check if which one of these logarithms are defined and which one of these are not defined. So a is not defined because we did this so many times now. Not defined because base a equals 1. Let me write down the rules for you again so that you can see it more clearly on this slide. So the rules are for log a of y to be defined. Rules are as follows. We have 1, y should be greater than 0. 2, a should also be greater than 0, and a cannot be equal to 1. So in our case, we saw that, well, a was 1, and that was the problem. 2 log 1 of 3, same reason, not defined because base equals 1. 3, I'm sorry, this should be a, this should be b, and this should be c. b, and that should be a. In c, the base is fine, so the base is 2, and that's completely okay. But we see that the y in this case is minus 8, and we know from our rules that y must be greater than 0. So y is not greater than 0. Y is not greater than 0. Let me write that better for you. y is not greater than 0. It's less than 0. It's minus 8. So this is not defined because y is less than 0. And D, same reason, base is fine, base is 2, it's greater than 0, and you have, oh sorry, base is 7. Base is 7, still greater than 0, minus 3, big problem here, y less than 0, that's a problem. That's a problem. Compare this with the first rule here, and you'll see that this is a problem. Okay, hopefully now the index form is also stuck into your memory. You know when log a of y is defined, you know why log 1 of 1 is not defined, you know why y should be greater than 0, and you know why the base a has to be greater than 0 and cannot be equal to 1. Moving on, let's talk about exercise. Okay, let me switch to a red pen. On, let's talk about a new exercise in your chapter 3 on logarithms, section 3.4. So exercise 3.4, and it's called common and natural logarithms. It's nothing new here, it's just names for certain kinds of logarithms with certain kinds of bases. So let's take a to be 10. Okay, then we can write the equation ax equals y as 10x equals y, and this is once again index form, power form. We can write this into log form as log base 10 of y equals x. Now whenever you have the base as 10 here, a equals 10, the logarithm is known as the common logarithm. So log 10 is known as the common logarithm. Okay, and there's a short form for this common logarithm. So log 10 is just written as L and G. You don't really need to memorize this now. You'll see it so many times that it'll just stick in your head. Okay, so the common logarithm is just log to the base 10. Some examples, of course, would be 2 equals log base 10 of 100. That makes sense because, as I've said before, the logarithm is just a power. So it's just raising 10 to the power of 2, which gives you 100. And you can write this in either form, index form or log form. So you can shorten this by writing LG in place of log 10. So log 10 becomes LG. Also write it backwards, LG 100. Another example would be, let's take it in index form. So 10 to the power 3 equals 1000. That's index form. You can write this in log form as log 10 of 1000 equals 3, and then you can abbreviate it to LG 1000 equals 3. Okay, so I hope that's clear. If not, don't worry about it. We'll see tons of examples of log 10 being written as LG in the future. Another logarithm is called the natural logarithm. And to talk about the natural logarithm, we must first talk about sequences. We won't talk too much in detail about sequences because it's just way above the scope of this course to talk about sequences. Maybe you'll see them in like advanced level mathematics, but definitely not here. So one sequence is given by just this collection of numbers 1, 2, 3, 4, 5, 6. Another sequence is given by 2, 4, 6, 8, 10, 12. Another sequence is given by 5, 25, 125. You get the point. Like these examples are sequences. Examples of sequences. Okay, this sequence can be written as n, just simply n, where over here n equals 1, over here n equals 2, n equals 3, n equals 4, so on. This sequence here can be written as 2n. Over here n equals 1, n equals 2. So if we place 1 in the place for n, we get the first position of this sequence. If we write n equals 2, you get the second position of the sequence. You write n equals 3, you get the third element of this sequence. N equals 4, you get the fourth element of the sequence, so on and so forth. This sequence can be written as 5 to the power of n. So when n equals 1, you get 5. When n equals 2, you get 5 squared, which is 25. And when n equals 3, you get 5 cubed, which is 125. Now, let me change the color. Another sequence is given by this formula, or this 1 plus 1 by n all raised to the power of n. Okay, let's see what happens when n equals 1. When n equals 1, you get 1 plus 1 over 1 power of 1, which is just 2. N equals 2, you get something like 1 plus half the power of 2, which is 3 by 2 squared, is 9 by 4, that's 2.25. N equals 3, you get 1 plus 1 over 3 the power of 3, that's equal to something like 4 by 3. That's 56 by 27, and that's equal to 2.074. Well, when n becomes very large, so say infinite, then you get a number that is called e. Okay, it's called e, the exponential. Very often in mathematics, you will see this number e popping up. Okay, it was this coming through from this sequence. N approaches infinity, so n becomes very large, and 1 plus 1 approaches this number called e. Roughly 2.71828. Roughly. It's not its exact value, but roughly. Well, at least when I was at your level, this is the value I had memorized for e. So if the base a equals this number e, then writing log of e is, then log of e basically is known as the natural logarithm, or the natural log. Let me switch back to the red color. So for example, and also one more thing, you can write log of e as just ln. Okay, so for example, if you have e raised to power x equals y, then this is the same as writing in log form log of e y, and from the abbreviation we can write this as ln. So let me make this clear. ln y. Got the x here. Okay, let's look at some examples. So one example would be, what should I write? E to the power 4x equals 21. Log form, we write this as, I'm not writing log form literally here, but it's log form. Okay, this equals to log of e. 21 equals 4x, and x equals, I mean, you can write this log e here as ln 21. ln x equals ln 21 by 4. Okay, so in your own book, in exercise 3.4, there is question 23b that we can look at. It says, given e raised to the power 1 minus y equals 3x, you have to find x in terms of, you have to find y in terms of x. Problem? You can write this in log form as log, one second, log of e 3x equals 1 minus y, and then we can write the log e as ln 3x, and then we can bring the y to the other side and write log y equals 1 minus ln 3x. That's one answer. Another example would be same exercise 3.4, question 24C. Uh, yeah. Okay, so that's ln x equals log 2. So this question is really good because it has ln and lg. Okay, so it has something that's base 10 and something that's base exponential. Okay, and what you have to do is solve for x. So how do we do this? Okay, so one thing to realize is that, well, this equation has one unknown. Let me change the color. So the unknown here is x, and this equation has no unknowns. The equation here has no unknowns. It's just lg of 2. Okay, so what you can do is bring this into index form. So you can write this, or basically a better way of doing this would be to once again realize that this is a logarithm, and that the logarithm always gives you the power, basically the index. It computes the index, and this equation here, this whole thing here, is already written in log form. And you can expand the ln x to write it as ln x is equals to log e of x equals lg of 2, and your base here a equals e, and y is just x in this case, and the power is, or exponent is, lg of 2. Okay, this is a little tricky to read this equation, but because both of them have logarithms attached to it, but if you look at the equation ax equals y going to log a y of x, then if you look at this equation, on the left hand side of this equation we have ln x, the base a is just e. So let's look at this equation. Look at it from, so the base here is e, here's your base, just a, and your y is now replaced by x. So color for you, x replaced, oh sorry, y is replaced by x, and you want to have a power as well. So this x, which is the power here, that x is just given by lg2. Okay, so ln x lg2, straightforward. You can just write this as e raised to power lg2 equals x. I hope this made sense, because it's not easy to see when you've just been introduced to logarithms. Don't worry, we'll see many more examples of this. We can look at one more example before we move on to the next exercise. And this example is coming from exercise 3.4, sorry. And it's not sure like which exercise this is. I think it's 23F. Please check it out. If I'm wrong, correct me. It's ln of x plus y minus 4x equals 0. And the task is to find y in terms of x. So we can write this as ln x plus y equals 4x. Okay, so remember equation and the previous equation, they both were in log form. It's also in log form. Then we know that this is just log of e x plus y. I won't always be writing log of e for ln. This is just to show you that, make you get used to the fact that ln is just log of e. And then we can go to index form by writing e raised to the power 4x equals x plus y. And this implies that y equals e to the 4x minus x. Okay, that's enough for examples. Let's move on to the next exercise or next section in your book, which is exercise 3.5. It's a very important exercise called laws of logarithms. So I'll mention these laws down. I think there are around 5 laws, but I will not prove them right now. And those who are interested in the proofs can look at the next lecture. All the proofs will be mentioned in the next lecture. They're not really important for you right now in this course, but if you feel that you really need to know the proofs before you can actually use these laws, then please refer to the next lecture. So the first law is called the change of base law. So I'll use a different pen color. Called the change of base law. And it's given by this: if a comma b comma c are greater than 0, all three of these, a, b, and c, are greater than 0. And of course, if a is not equal to 1 and c is not equal to 1, then log a of b is equal to log c b divided by log c a. So this is the rule. If a, b, and c, all three of these are greater than 0, they're positive. And if your base a and your base c are not equal to 1, then log a of b equals to log c of b divided by log c of a. Okay, let's take an example first, that we get used to this rule. And let's first talk about a special case, and then we can see examples actually. So what happens if c equals b? Well, then log a b equals log CB, just using this formula right here, log CA, and this is equals to if C equals B, log BB and log BA. Now what is log BB? If you already know the answer, great, means you've understood the log form basically. But what is log BB if you don't know the answer? Well, just convert this into index form and you'll see it. So in index form, this is just given by b raised to the power x equals b, correct? B to the power 1, and this implies that x equals 1. So the logarithm here, log BB, is just the exponent to which you need to raise this b to get this other b. So this is, so log BB is some exponent x, and we already know what this exponent is. It's just x equals 1. So log BB here till here is just equals to 1, because if you raise b to 1, you get itself b. Okay, I hope this makes sense. So over here you have log b of b, that's just 1, and log b a. I mean, think about it. What would you raise b to get b? You would raise b to 1 to get itself back. And that's what the logarithm is. It's just a tool to compute the power. Okay. So we know what happens in the special case. We know the formula. Let's switch back to the two examples. One way to get used to this formula is just to evaluate these terms here. So log 7 5 times log 5 9 times log 9 7. The first one, log 7 5, can be written as log 10 5. Okay, maybe I'm going a little too fast here. Let me just make it easier for you. So the rule was, let me write the rule. Green pen. The rule is this: log AB equals log CB over log CA. Okay. So right now in this log 7 5, we see that A equals 7 here and B equals 5. Okay, A equals 7, B equals 5. So we have log 7 5 equals log AB equals 5, A equals 7. Now using this rule here, we've highlighted green, we can take C to be equal to 10, and then we can write log 7 5, take C equals 10, write it as log 10 5 and log 10 7. Okay, so we'll take 7 in each case now. That was for log 7 of 5. Now we can do another for log 5 of 9. This is this term right here. We can take C again as 10 and write this as log 10 of 9 over log 10 of 5. Then we can do the same thing for log 9 of 7. This is this thing right here. Take C again as 10. So log 10, 7 divided by log 10 of 9. Okay, let me write this down more clearly for you. I hope this is becoming easier and easier for you as you see it. So now I'll just stick with the red pen. So the stuff that we needed to evaluate was log 7 of 5 times log 5 of 9 times log 9 of 7. First term we wrote as log 10 of 5 log 7, log 10 of 7. If you don't understand how this came about, then just go back a few seconds ago and see how we got this from the rule that we wrote in green. Times this can be written as log 10 9 log 10 5, and then this for this we write log 10 7 log 10 9, and we can write this in LG form as well, right? Because this log 10 is the common logarithm. So common logarithm, no one really uses this word for it when they speak about it. They just say LG or log. People usually refer to this as log rather than log 10. So LG 5 LG 7 times LG 9 LG 5 LG 7 LG 9, and then you can just cut this with this and this with this. The answer is just 1. Okay, pretty long computation for such a boring answer. Okay, so that was the first law, and that was just the change of base law. So you basically change the base. So in these cases we see like our base was 7 became 10, and then the second term we see that the base was 5 and became 10. Same thing for the third term as well. So I'll start a new slide and we can talk about the second law, which is the product law. Very important law, and you'll use it all throughout your O levels, your A levels, definitely beyond your O and A levels as well. So the second law, you write down law properly. This is the product law. You write down product properly for you. Okay, and law goes as follows: if A, X, Y are all positive, and of course we've discussed this many times, A cannot be equal to 1, then log A of X times Y is the same as log AX. Let me write this properly. Sorry about this. This is the same as writing log A of X plus log A of Y. Okay, So let's do a few examples, because the more examples you do at this level, the better you will get. So one, let's try log 3 of 49. This is equals to, using this is equals to 7 times 7, and using the law above, the product law, is equals to log of 3 7 plus log base 3 of 7, 2 log 3 7. Another example would be log 3 of 9. That's the same as writing log 3 into 3, and that's the same as log 3 of 3 plus log 3 of 3, and this we know is 1, and this we know. Okay, I'll explain why this is 1 again for you, so that you remember it and you can use it whenever you see the number 1. So the logarithm computes the power. Always remember this: the logarithm computes the power. Never forget this. So, to what power would you raise 3 to get 3 again? So basically, what I'm asking you is, to what power would you raise 3? So I write x there to get 3 again. Answer is x equals 1. The logarithm computes this power. So the logarithm computes is this x. So 3 raised to power x equals 3 can be written as log 3 of 3 equals x. And we know x is 1. So log 3 of 3 computes this power, which is 1. Okay. If you go back a few seconds, you'll see me writing 1 for log 3 of 3. And this is exactly why I write 1 in that place. Okay. Another example would be log 4 of 2 plus log 4 of 8. And we can use the rule in reverse, basically the law in reverse. Let me write the law again. The law is this: log a xy equals log of a x plus log of a y. Okay, just remember this. So we can use this in reverse as well. So if we see over here that what's written in red has the form of what's written of the on the right hand side of the equation in green. So we can go backwards. Just go this way. So we write this as log 4 of 2 times 8. That's log 4 of 16, which is 2. Now, probably wondering, why did I write 2 for log 4 of 16? Same thing, the logarithm computes the power. So log 4 of 16 is some power. Let's write it as, what should I write power as? Let's write it as x. Let's write it as x. Okay. So in index form, this is written as 4 to the power of x equals 16. So the logarithm computes this power. Okay, it's just equal to this power. So 16 is just 4 raised to 2. So x is just 2 here. The logarithm computes this power. So log 4 16 is just 2. Okay. So we used this law in reverse and we saw that the answer is 2. Now just remember this, that the answer was 2. I could ask you another question just from this by knowing that the answer is 2. So the question was log 4 of 2 plus log 4 of 8. Sorry about this. Is, we know that it's 2. Now if I ask you what is log 4 of 8, so you know it's some number because the logarithm computes the power and that's a number. So how would you compute log 4 of 8? Well, what is log 4 of 2? This term here. What is this term? So this is also some power, and you can write this as, it's some number basically. You can write this as y. So and this is log form basically. This is log form right here. And you can make this into index form by saying 4 raised to the power y equals 2. So what should y be so that if you raise 4 to that number, you get 2? This is the same as writing 4 to the power of half. Correct? Because if you take the square root of 4, you get 2. The positive square root of 4 gives you 2. So you see that, and this half basically just means square root. Basically, this half is just a square root. Don't get confused by this. This half is just a square root. Okay, so 4 raised to power y is just 4 raised to power half, which is 2. So just copying things down from here. And from this we see that y equals half. Okay, so log 4 computes this y. Log 4 computes this, log 4 of 2 computes this y. So log 4 of 2 is half. And from this equation 1 here, if log 4 of 2 is half, then you have half plus log 4 of 8 equals 2. And this gives us that log 4 of 8 is equals to 3 by 2. It's 1.5. So log 4 of 8 is we realize that log 4 of 8 is, from our calculations, is 1.5. So in index form, this is 4 to the power 1.5 equals 8. Just use your calculator and raise 4 to the power of 1.5 or 3 by 2 and check if it's 8 or not. If it's 8, then you're correct. If it's not, then definitely made a mistake. But I doubt that we've made any mistake. Okay, so the next rule, or maybe we can try some more examples. Not sure. Try some examples. Yeah, actually, I can give you an example so that you can try it yourself. So, example. So, simplify. Let me write this in a style that everyone can understand. Simplify log 2 of 40 plus log 2 of 0.1 plus log 2 of 0.25. I'll just tell you the answer so that you know when you're wrong and you know when you're right. The answer is 0. Okay. Next we'll talk about quotient law, law 3. Okay, let me change the pen color to green. So law 3, which is called the quotient law, it's exactly like the product law. It's just the product law with a minus sign, basically, when you have a quotient. So if a, x, y are, this is an x greater than 0, and of course a cannot be equal to 1, then log of a x by y same as log a x minus log a y. That's law number 3. You can look at the proof for this law in the next lecture.